Welcome to Amber Book, 40 Minutes of Competence. I cannot tell you how excited I am to be here. I totally geek out on this stuff, all of it, every bit of it. I love studying it, I love talking about it, and I'm glad you're here joining us. So, in 2007, many of you know that there was a shooting at Virginia Tech. It was at the time the largest mass shooting ever. It's still the biggest school shooting. And people were pretty jumpy right afterward. 32 people died, including one of our architecture students. And so they hastily put these things up. And ostensibly they're there to show you the time. They always show you the time. But they were put up so that the university authorities could warn you if there was a problem again. And they could send messages. But because it was put up hastily, all over campus on these things you see these. And we're going to talk about what those are. All right, so today is electrical raceways, and the question is, if you have a desk and it's somewhere kind of out there in the middle of the floor plate, how do you bring power to it? And this is a question that you wouldn't think is that important for an architect to know. I think I've mentioned in the videos, as those of you guys who've seen them, I've mentioned many times in the videos that I don't think most of electricity is that important for architects because it doesn't affect the architecture of the building too much. However, this happens to be one of those topics that it seems kind of stupid at the beginning. Why would the NCAR folks even care? But it's actually many topics are like this. As you get more into it, you realize that there are an inordinate number of choices for bringing the power deep into the floor plate. B, we need more power and we have bigger floor plates than we have historically. And most important, C, is that it has a huge impact both on the cost and a hegemonic kind of outsized impact on things like floor-to-floor heights, really important things for architects. So while this seems like maybe kind of a spec writing issue or kind of a late design issue, it's actually a pretty early design issue, or at least it should be. So we generally run if we're not in a house, if we're in something bigger than a house, we generally run our electricity through conduits. It could be steel, could be aluminum. And those conduits serve several purposes. They protect the wire in case you happen to run a nail through the wall to hang a picture and it happens to hit a wire. So they protect the wire and they protect the building from the wire if there's a short and things start to heat up, and they act as a ground. You'll have to, maybe on another day we'll talk about what a ground is and why it's important, but they act as a ground, which makes our electrical system safer. And they support the wire as it goes through. Now generally, if we're not talking about a concrete building, we can run these pretty easily into the middle of a floor plate. But if we're talking about a concrete building, it gets much more complicated. So we have junction box, we have conduit, we have junction boxes, and we have more conduit, and we have flexible conduit. You see here flexible conduit, and the flexible conduit allows us to make turns that might be kind of difficult in the rigid conduit, and it also allows us some flexibility, some tolerance, so that the lighting contractor doesn't have to coordinate quite so closely with the conduit people to be within, some tiny fraction of an inch, because it gives us some flexibility. And inside the conduit is pretty much what you think. I mean, it's just a pipe with wire in it. So there happens to be some missing plate there. And what we're sending is low voltage kind of signal wire to this thermostat. So that thermostat needs to be able to get some power and send some signal back. And it's done with just a wire going through. I'm not sure what this one's for. It's probably for an older version of the thermostat. Maybe something when it needed data or something. And if we have conduit and it penetrates something, like if it penetrates a fire-rated wall, we need to put fire stop in it because we want to make sure that fire in this space here doesn't go into that space. And generally when we have fire-rated walls, which again is the topic of a past 40 minutes of competence, it's generally going to be because we either have a chase in the wall that connects between floors and we don't want fire and smoke to move between floors. That's the case here. or because we have different occupancies. If we have a restaurant on one side and multifamily residential on the other side of that wall, and we're penetrating it, we generally are going to have a fire rated wall, and as part of that, all penetrations are going to have to be sealed up to fire. But you'll see, that's right here, but if we have a non-fire rated wall, especially one that's non-structure bearing, non-load bearing, we can run right through the wall with wires and it's no problem. And you see there, sometimes we just have these things loose. We don't have any of the coverings that we're about to talk about. All right. So if we want to bring, power to that desk or some desk in the middle, or this desk out here, some desk in the middle, and we have a concrete floor, it turns out it's not super easy, and there are some significant architectural trade-offs. So one way we can do it is we can literally just cast it into the structure. So if it's a new building and we know about it, we can run the conduit into the structure itself. We're typically going to run the conduit on the bottom half of the slab if it's a slab that spans. And we do this for the reason you think. We do this because, for the same reason we put rebar down there, because concrete is pretty lousy in tension. And if we have some steel we're running through there anyway, we might as well get some tension benefit so that when the floor wants to sag and there wants to be more tension, the floor wants to kind of do that, and there's more tension at the bottom and compression at the top, we want to put it at the bottom of the slab. Now, how close to the edge of the slab can we get? In other words, can we run conduit right here or right here? No, we can't. We need to have at least, if this is our slab and we have conduit here, we need to, and this is concrete all the way around it, we need to have at least 3/4 of an inch clear, otherwise it's likely to have some cracking. And you may have people who tell you it's okay. I've seen buildings where it doesn't crack when it's less than 3/4 of an inch, because floor to floor heights, as you might imagine, become kind of a big deal. And as you might imagine, architects often don't coordinate or didn't plan on as much conduit as there tends to turn out to be. And it gets really hard to fit all the conduit in. And someone will say, oh, don't worry about it. You can get it a little closer than 3/4 of an inch. I've seen buildings where it's okay. And there are lots of buildings where there's no cracking, but there are lots of buildings where there is, so don't listen to them. And if you have multiple conduit, the space between them on center is greater than 3 times the diameter of the bigger of the conduits, that being the diameter. So greater than 3D if that's D. But you don't have to memorize those. Those are not, those kind of numbers are generally not worth memorizing, with a few exceptions, like the number of square feet in an acre and the number of the kind of numbers that have to do with ADA accessible slopes are probably worth memorizing, but most numbers like this are not. I'm just telling you so you know. Now, if you have a picture of a project you're working on or have worked on where the conduit does not meet these rules, because it's quite common, send that picture to me, because I don't have any pictures of that. So send me that picture and I can then share it with other people. All right, so if we're running it through the structure, like I said, we can run it just as conduit in the formwork, and you can Google that to see images of that. Or we can do this, and this is called, excuse me, this is called, I want to get it right. A cellular metal floor raceway. A cellular metal floor raceway. Let me write this down. Cellular. And what they are is they're proprietary, off-the-shelf kind of products, and they include everything you need to pour your slab, including the metal pan, including the shear studs, including the kind of steel structure you might need to run up to pour a slab. But it also has these cavities, and it has cavities for primary feeds that go one way, and then secondary feeds that pull off those primary feeds that go the other way, and they're going to go to electrical receptacles and data receptacles all around the middle of the floor. And by doing so, we can bring the power to the desk in the middle of the space. Now, all of these underfloor systems are going to be expensive. Typically, something on the order of 50% more for the electrical than it would have been otherwise, but some are more expensive than others. This is obviously only acceptable for a new building. You couldn't do this for a renovation, but if it's a new building, this is probably a pretty good way to go. And this is what we did here in our studio. All of these pictures I took one day in our studio. It's amazing when you start looking for this kind of stuff, how often you can find different flavors of it, often in the same building. So here we have the plates, the access plates that go like this, and then there are other kind of intermediate access plates here. And then from that primary feed, we're going to run our secondary feeds perpendicular to them, like this. And that's what's going on here. So we had, in our studio, we had circular ones instead of rectangular ones, but you get the idea. So here's the main feed, and kind of zooming into it, you see it right here, and then you see those secondary feeds are going to go out, and they're going to feed those electrical receptacles where they are. And here's an example of an electrical receptacle. It's underneath the desk, and then we can plug something in. In this case, it's like a desk lamp, and we can have our power strip at our desk. Now, the legend of this is an underground building, and the legend of this building is that the reason these pinup rooms are so low ceilinged, there's only 7'6" between the floor and the ceiling, clear space, which means code, but it's really, really small. When you're in there, it feels like it's pretty claustrophobic, and the legend is that the folks that designed it did not account for the thickness of the slab they accounted for the thickness of the slab as it needed to be for structure, but not for the extra thickness of the slab, the extra 6 inches or so thickness it needed to be to handle all that conduit moving through the concrete slab. So it raised the ground floor, which lowered the clearance underneath the ceiling. So that's the first option, or I guess that's really kind of the second, cellular metal raceways. The first option was just running the conduit in the slab itself when you pour it. If the slab is already poured, or even if it's not, you can run what are called ducts. And ducts, they sound like they're for air, and of course we do have air ducts, but these are the metal ducts that are in here that we've sawed out and then kind of refilled back in, and they are just for wires. So it's just like a duct but for wires, and you can see it right there. So it's coming out of the wall, and then you have electrical receptacles, and you can kind of pretty clearly see where they did it going through, and it's probably not a coincidence that this is the ground floor. So this is a slab on grade, so we can dig it up without really having to worry about sawing across any post-tension for the concrete or doing any damage to the structure, because this concrete slab is not spanning, it's resting on the ground. Anyhow, this is very expensive. We generally don't do that anymore if we don't have to, but we sometimes have to. Now, another option is to do it, so our first kind of category was to do it inside. So we did it as ducts in the floor. We did it as a conduit that's just kind of buried in the concrete, and we did it as those proprietary metal pans that are cellular metal raceways. Cellular metal floor raceways. But what we're dealing with now is kind of a different category, and it's going to be on top. It's going to be just kind of on the surface. And so one other thing we can do is we can run conduit on top of the structural floor, like if we have a renovation, and then pour a concrete topping on top of that. Again, just making sure that we have at least 3/4 of an inch of concrete topping on top of the top of our highest conduit. And we can do it on the floor just as a kind of a little thing that just sticks out, a little thing that just sticks out. The same type of thing we see here, which are actually metal backed floor channels, or in this case a wall channel. They're called metal backed because they're backed by metal, even though the front of them is plastic. And you see it here on the wall. I don't have many pictures of it on the floor, but you've seen it lots of places on the wall. You see it here, and then this is for data and for electricity. Sometimes we don't bother using it at all, and so it's ugly with them and it's ugly without them. These things are pretty nasty in general. They're kind of gnarly, but it's gnarly when we don't use them also. So we have them here for a fire suppression system or fire detection system. And sometimes we can put them on the floor, especially if we don't mind people tripping and we don't mind areas of the floor getting kind of dirty. So generally this is not the best option, but sometimes it's all you got. It's certainly an inexpensive option. It's just a bit harder to maintain, and you can have a tripping hazard if it's a place where a lot of people walk. Our next option for going on the floor is pretty clever. It's under carpet, and it's basically like a tape. And so what we're going to do, and you can go ahead and Google it to take a look at it, but underneath this carpet, there's a tape. You can YouTube it, because you can see how it's installed. It's pretty interesting, but it's really thin tape. It's 0.03 inches thick, and it's connected. If I'm zooming into this tape, maybe it looks like that, and the conductors are flat and long, and we can run those 2 spots in the middle of the floor, and then we can plug into that. And the advantage of that, of course, is it's not very expensive, and the other advantage is it doesn't change our floor to ceiling heights, because we don't have to pour concrete topping. We don't have to make everything thicker to account for a bunch of conduit. We don't have to put things in conduit. The disadvantage is that you have to have carpet, and so if you hate carpet, and if you ever want something other than carpet, you're going to have to come up with a retrofit to get electricity to your building or to your floor. But also, the disadvantage is, it's not really a disadvantage, I would say it's a limitation. We generally don't use these tape systems, these under carpet systems. We generally don't use them unless it's a pretty small room that we're dealing with. So if we have a really big room with maybe 100 receptacles or something in the room, that kind of electrical demand typically requires bigger conduits than we can fit in the tape. It typically requires junction boxes and kind of bigger electrical equipment than is safe to just run with tape under carpet. But we can run under carpet from something that has more juice. We can run it as kind of a tertiary, tributary kind of thing, just not generally main wires that are going to serve a whole bunch of receptacles at a time. And then you've surely seen these raised access floors. So there'll be these tiles, kind of, and they'll be on pedestals, adjustable pedestals, and they're typically the tiles themselves are typically 24 inches by 24 inches, and the tiles sit typically between 12 inches and 24 inches above the structural floor, and they've become popular. In 2007, we did a renovation for this studio, and we have this raised access floor, and we have this terrazzo floor for our lobby slash exhibit space. And so we have this really kind of cheap looking I don't know if it's vinyl or some kind of composite. It has kind of a hollow linoleum feel, but it's just a little ramp. And you can see that this is higher, this level here is higher than that level here. It's not the 12 to 24 inches I described to you, in part because I think this ramp would get a little steep. So they may do with just a few inches, but when you're walking on it, there's me walking on it. When you're walking on it, it's pretty, it's just unsatisfying. It's got a kind of a hollow thump. It certainly lowers your ceiling height, but it does allow you to get electricity into the middle of the floor, and it's flexible. You can use these little suction cups and pick up any one of these tiles quite easily. Now, as an aside, I have become disenchanted with flexibility in architectural products for two reasons. A, they tend not to be that durable when they're flexible. Three reasons. B, they're pretty expensive for what they are usually, but they promise flexibility. But mostly because we generally don't change things around. I mean, we have moved the desks in the studio around every single year. In fact, we're moving them around right now as I record this. And I can tell you now, there is a 0% chance that anyone's going to move the electrical receptacles to adjust to the new desk setup. It's just not worth it, and it's not that big a deal to run a cable here and there. And in office buildings, we often don't rearrange the furniture that much. You know, these expensive and ugly cubicle farms systems are set up, and they're sold as being flexible, but generally, once they're in place, they're usually not rearranged, or at least not much. So anyhow, I am off flexibility. I think it's not that important. And then you also have, with any of these, not just with this one, with any of these underfloor electrical raceways or systems, you have a cleaning issue, which is that dirt just by gravity is going to get in there. So here we are 12 years in, and it's pretty nasty. And then you see, you know, this isn't really, they're not even anymore. You know, there's just like a little ledge there, a little lip that you may see that I'm kind of going over. You can see that right there. I'll zoom into it. It looks like that. So you get these kind of problems that, frankly, probably would not be there if the whole, if the whole floor was terrazzo at the same level. But it has the advantage that students need, of course, to be able to plug things in on their desks. Their desks are in the middle of the floor, far from walls. And if you're far from a wall, you have just a bunch of bad options to bring electricity to, either expensive and disruptive or inexpensive and ugly. And so here it is in my office. Again, there's a data cable here. Here it is in my office underneath the bookshelf. That I don't know that I'd ever be able to take that off. I've never taken it off up until now. Here it is in the carpet, but this is not an under carpet system. This happens to be a carpet that's on top of one of those little floating floors that I just described to you, one of these raised access floors. So you, just because you have a carpet doesn't mean you have an under carpet system. You can have a raised access floor and then put carpet on top of a portion of that or all of that. All right, and then we have through the ceiling below. So what we can do is, if we have a desk here and we want to bring electrical receptacle to here, we can, underneath here we have all kinds of conduit for the lights in the floor below. And so what we can do is, since we have conduit anyway, we can kind of just punch a hole through it, and we can run our conduit through, and we can have our electrical receptacle available to the desk in the middle of the floor. And this conduit in the ceiling of the floor of the story below can either be exposed or can be underneath some kind of a hung ceiling. But either way, the advantage of this, of course, is that we don't have to reduce significantly our floor to ceiling height, at least not on that floor. And on this floor, we probably, the floor below, we probably not reduced it very much, just the thickness of that conduit that probably had to be there anyway. It's fairly expensive because you have to drill a bunch of holes in through the structure, and you have to make sure that you're not drilling through things that you shouldn't be drilling through if it's a retrofit, or you have to sleeve the structure if it's a new construction. And of course, if this is fire rated, which it often is, especially in concrete structures, we often use concrete structures when we need to fire rate the floor to floor. If that's fire rated, then we're going to have to seal it up with that fire stop to make sure that the smoke from the fire down below is less likely, the smoke and fire is less likely to jump through to the story above. But anyhow, we can go through the ceiling, and so it looks like you're looking at a bunch of electrical wiring for maybe for the lights that you see here on this floor. This is the first floor, but actually if you look carefully here, you see that this is being pulled off to serve the floor above it. So this is being pulled off to serve the floor above it, and that way we can bring electricity to the floor above in the middle of the floor without having to raise the height of the floor above it. And like I said, it could be below a dropped ceiling. Or finally, we could hang it from the ceiling above. So we can do it on like this, and these things are pretty cool, except for the photos I see of these things are always like when the building first opens and they all look kind of clean. I wonder what they look like when they're all tangled together and they're all pulled down. And so if any of you guys have pictures of these things in use that you can take, please take one and send it to me, because I would love to be able to share what these look like after time. And if they look good after time, show me that too. I'd love to see it. But we see these in offices now. We've long seen these on factory floors and other industrial buildings when we needed to bring electricity to the middle of the floor. And then we have these poles, these floor-to-ceiling poles that also can drop down from the ceiling, and they're exactly what they sound like. There's data, there's electricity, there's power availability, there's data, and for some reason there's two poles together here, but you get the idea. And floating in the air is what we just saw. Floating in the air are these baskets. So typically this is more common with data. The code often doesn't let you put live electrical wire that could really hurt you if there was a short or if someone cut through it in the basket, just kind of floating there. But this building was built in the 50s, and of course they had no way to anticipate how much data would be required. They probably didn't even think about data, because there was no such thing as wires for data back in the 50s. And so you wind up with these floating baskets to hold the data wires kind of everywhere. And if they're going through something, this one happens to be just going through a wall that's not fire rated, but if it is ever, and here's a whole bunch of data, if it is ever, and here's some trash up there that someone threw up there that'll be there till the day I die. But sometimes you have to go through a rated wall. So we have these little kind of bricks that we'll put around the data, so that again, this is a legal, kosher, appropriate way to allow for data cables that have some flexibility. In other words, if we want to run another data cable, we can. We just take out one of these blocks and then run another one and then put it back in. And so we still maintain our fire separation, but we do so in a more flexible way. And this is often done in the theater as well. If you imagine in the theater, there's always different cables being run through for different microphones or lighting for performances, and so they'll have all kinds of pillows and bricks like this that seal up a wall in a way that separates it. All right, that concludes that. For next class, for our next meeting, is in steel structures, what types of lateral bracing do we use? So what are the different flavors of lateral bracing? So we're trying to resist wind forces and seismic forces. And what are the relative advantages and disadvantages of those different types? So that's for next Thursday at 2 o'clock, at 2 p.m. I'm going to talk a little bit about our chat question from last week, and then I'll open up the floor. Someone said windowsill is a huge problem for thermal bridging. How do you resolve? So thermal bridging, of course, is when you have, well, let's make a wall. We have a wall here. And we have the continuation of that wall, and we're looking, it could be in planar section, but let's say it's in section, and let's say it's a double hung window. And we have a sill. And of course we have kind of the frame of the window itself. So there's all kinds of thermal bridging questions here. And a thermal bridge, there were some other questions last week about what a thermal bridge is, and I covered that in a previous week, so I'm not going to get too into it. I guess if this is a sill, this must be outside because we've sloped this down to the outside. I feel like a double hung window might generally have the sash on the inside, but you get the idea. But there's a bunch of, the frame itself is a path of thermal bridging. So if this is a aluminum frame window, then we want to put a thermal break in it if we can, especially if we're in a cold climate. We'll put a thermal break in that window, which is essentially like a piece of rubber between the two halves of they'll split the frame in two halves and put a piece of rubber between, so we have less conduction going out. Or we won't use metal at all, we'll use something less conductive like vinyl or wood. And then of course this is a big thermal bridging and air infiltration problem for any kind of place where these two things slide together. And then the sill itself can serve as something that acts as a thermal bridge. So generally, if it's concrete or steel or metal of any kind, or brick or stone, it's going to be a pretty good thermal conductor, which is, and by good I mean bad, because if it's cold, if it's 0 degrees outside and it's 70 degrees inside, this heat is going to be moving it, kind of working its way outside. It's going to be working its way outside through that sill. And so one thing we can do is we can use a less conductive material. So we can use something that's like wood. We can put a thermal break in here. We can put a thermal break in there, and that will, and the thermal break again could be a piece of wood that's between precast concrete here and precast concrete here, or it could be a piece of plastic that's between wood inside and stone outside. You get the idea. We just don't want the same piece going all the way through. And generally, we want the window to line up with the insulation. So if we have insulation here, that works. Now, if we have our insulation is out here, if our insulation is out here, and our window is in here at this plane, then it becomes much more difficult. You wind up with more of an opportunity for having a thermal bridge. Thermal bridge is bad, thermal break is good. Much more important in cold climates than warm climates.
Hi Mike, can I ask you a question about just what you showed about the window for thermal bridging?
Sure. Oops.
So here you showed that two location that's like the seal and then the middle of the window, like where the two sashes are. How about the head of the window? Is that also?
Yeah, I mean, anytime that there's a transition, especially if there's structure in that transition, there's an opportunity for thermal bridging. So if we can, what we would like to do is we would like to have, you might be tempted to put a wide flange in there that looks like this, and then put that in there. But if it were me, I might consider putting two C-channels in there if there had to be a steel up there. And then what you can do is you can put some, we've talked about this before, you can put some wood in between them, or plastic, kind of rigid plastic in between them, and bolt that together. And in doing so, you've significantly reduced the amount of thermal bridging going on.
Okay. So it's mainly the window that's most of the thermal bridging.
No, you mean it's mainly in this assembly it's mainly the window, or you mean in a building it's mainly windows?
In a building?
No, it's not just mainly windows. It's anywhere where anything that moves. Balconies are a big one. So if we have a balcony that goes over here, often that balcony is part of the same structure that's in here. So if it's 0 degrees outside and that structure continues its way through, so it's balconies. If you have an awning or some kind of an overhang here, that's tied into that structure. If you have sometimes just architecturally, there'll be some kind of shading element going in plan as well. Maybe it's like that in elevation. Anything that protrudes from the inside to the outside could be from a roof overhang. It can even be from the floor. If you have this kind of idea, maybe this is on grade here, maybe this is grade here, and you want to pour a continuous looking slab so that the control joints kind of line up in rhythm, and it looks like a continuous slab when you're standing out here and you're looking through. You may be tempted to actually pour a continuous slab, but of course there's lots of reasons not to do that, not least of which the one outside has to deal with moisture, so they need a different kind of concrete admixtures, but also and the one outside probably needs to slope away from the building to bring water away from the building. But even otherwise, just from a thermal bridging point of view, you would want to put some kind of a break in between, and make sure it doesn't come through. So windows are certainly one of the biggest sources of thermal bridging in many buildings, but it's by no means is it the only one. And the thermal bridging, it's one of those concepts that once it clicks with you, you're like, oh, it just clicks. So basically, what you want to be able to do is you want to be able to run. You take a highlighter on your plan in your section of your building and run a continuous line down through and have insulation be continuous. Never like have your marker always be on the insulation, and being able to go all the way around the enclosure of your building without ever having to pick up your highlighter, and your highlighter is always on insulation. So wherever your highlighter is not on insulation, that's a path for thermal bridging. And then you have to decide based on how high performance your building goals are, and based on how expensive and difficult it's going to be. You have to decide, and not insignificantly based on how cold your climate is, you have to decide whether it's worth really putting a thermal break in there. So for instance, if you have a footer underground on a building, and you have a slab for your basement, so we're underground here, and your insulation maybe comes down here, underground, so this is also underground in section. And you may have also have insulation here, rigid insulation under the slab. If you have a cold climate, that's not so unusual. Well, now of course you have a thermal bridging path through here. And so what we're seeing more and more of is people are continuing this insulation down to here, and this insulation down to here. And then they have this kind of, it's non-compressible, it's basically a structural insulation, so underground. So we've made products that can support buildings, at least smaller buildings, I'm not sure about the bigger ones. And so the insulation can go underneath the footer, and you can have something that's has enough air pockets to have insulation, but has enough structural integrity to actually be able to support that wall, and we can make it continuous. But the ground itself also provides some insulation, especially if you're 10, 12 feet down or something, 8 feet down. So there's some insulative characteristics of the ground, especially if there's a lot of it. So what winds up happening is, so first you kind of deal with the above ground thermal, well first you deal with making sure you have enough insulation and making sure you have air tightness, and then if you want to make it even better, you start getting into thermal bridging at windowsills, and if you want to make it even better, you kind of keep going for the next highest fruit, or next lowest fruit, I guess you would say. the next available lowest fruit, and you keep kind of working your way through the easiest things and the most effective things, which are essentially the biggest thermal bridges. Now, there will always be thermal bridges in your building. It's impossible not to have any. But when you get pretty close to none, the benefit really starts to go up pretty ridiculously. So you've put something, some hot soup in a thermos, and you brought it for lunch, and then you open it 3 hours, 4 hours later, and it's still warm, which is insane. And the reason you've been able to do that is because once you've really taken care of all the thermal bridging, you have continuous insulation all the way around. That's the stories you hear about. This guy built a house in Germany, and every morning he heats up a cup of tea, and that's all the heat he needs for his house for the whole day, and even in the wintertime. And so there are buildings like that that are so super insulated that those are the ones where you start worrying about, how does the pipe get in, bring water into the house so that it doesn't provide an unacceptable thermal bridge when you get to kind of that level of performance. But that's not a typical concern.
Thank you.
You're welcome.
I think let's not forget about the roof flat roof as well.
Yeah, if there's the parapet.
Roof drains.
Yeah, roof drains are a source of thermal bridging too.
Hi Michael, I have a question. My name is Paulina.
Mm-hmm.
One quick question, and then someone else in the chat had a really good question that I'm curious about. One is that you said that the floating baskets are not safe enough for conduits, but then are the other types you recommended, or that we were going through, like tape and under carpet, how are those safe?
Yeah, so, okay, let's hold on to your other question. Let's answer that one first. So first of all, they're safe for conduit, they're not safe for bare wire. So you could run conduit in them, I think, but you couldn't just run 120 volt, just insulated wire in it, because you would be afraid that maybe someone would be trying to hang something from it, and it might, rip it out or something like that. So we're pretty careful with big buildings now for having kind of exposed wires like that. Now low voltage would be a different story. Low voltage is like, what you use for like cable track lighting or something like that. That's a less dangerous exposed wire. So that's the first thing you said. But then you said, what did you say right after that? You had a good point.
Like the other methods we discussed, like tape or
right. You're like, how is that kosher? Because it's behind something that's kind of a quasi-permanent part of the building. So you don't have to rely. You're not as worried about people ripping up carpet and then slicing through wire. It's generally going to be building trades who do that. It's generally not going to be children exposed to that kind of thing. It's unlikely to be a problem, but it's still possible. It's definitely possible. Electricity kills people all the time. It's not unusual for electricity to kill someone. I don't know what the numbers are, but we can look them up for next week. But electricity is super dangerous. We're just trying to kind of say, just like driving. Driving is dangerous, so we say, okay, you have to use your turn signal before changing lanes, and you have to drive below the speed limit, but it doesn't make it completely safe. It just makes it safer than it would be otherwise. So we have drawn a line and said every building above this size needs to have, kind of conduit that's more or less protected for all the electrical elements. And every building below that size, maybe we can just drill holes in the studs and in the joists and run loose wire, not exposed conductor, but loose wire through there. Because have you ever set an exhibit up with a bunch of architecture students? Like, they will hang heavy things from anything. I mean, absolutely anything. Whether it be pipes for sprinkler heads, whether it be the sprinkler heads themselves, they will hang it from the cable, the track of the track that's used for the drop ceiling, for the acoustical ceiling tile. And so you start and that's people who ostensibly have some background in building and some comfort with kind of respecting buildings. And so you kind of multiply that out by someone who is trying to, pick themselves up to put some cardboard pick themselves up to the ceiling and trying to tape some cardboard over top of a duct that's blowing cold air out of a register, and they're kind of cold at their desk, so they'll stand up on a chair that has wheels on it in a dangerous way and kind of jump up onto the basket, and then be hanging on that, and it's that kind of thing that we're trying to avoid. We're trying to avoid knuckleheads. And we've all been that knucklehead. You just get really frustrated, and you just, if you've never been that knucklehead, you have been, you just don't know it. Someone else has thought you are. So what was your second question?
The second question is actually Erma's question from the chat, which I thought was very interesting, which was when doing penetrations on slabs or structure for the conduits, aren't they getting compromised structurally with those penetrations?
Yeah. Yes, they are. And so you need to bring, if it's an existing building, not the biggest issue that I know of is you're coring through a slab. Generally, you can core. Don't quote me on this. Don't say it's okay. Michael said it's okay. But generally, the issue isn't so much putting a single core in a big slab. The issue is there's a post tension in the slab. There's a cable that was put in when the slab was poured. And the way post tensioning works, of course, is if you take a floppy book, like the Amber book, and you squeeze it together from both sides. So here's the book. If I just push down on it, it'll curve. But if I squeeze it together from both sides, it'll be much stronger. And so the way post tensioning works is as the slab is poured, we're going to pour it with cables that kind of drape like this, and then we're going to put anchors on the ends of those cables, and we're going to use a hydraulic jack to pull those cables super tight. So we essentially are pushing the slab together, which means that when we step on the slab and put a gravity force on it, it's going to do a better job of resisting that gravity force without having a bending moment, without wanting to bend down. And if we core through and we break one of those cables, now our entire floor may literally collapse. Those cables, and they're under really high tension, so if you drill through it, it snaps and you've lost it forever. And so that is a huge problem. So we have these devices, I'm not sure what they look like, but I'm going to draw them as a box, that use, I think it's radar, maybe it's X-ray technology, but they essentially X-ray the slab to make sure that they know where those post-tension cables are, or in the case of precast concrete, they may be pre-tension cables. And so we're going to make sure you just never want to you never as like a tenant in a concrete building want to be like, I think we're going to put an electrical receptacle here. I'm just going to hire a guy with a drill to come out and drill it. You need to actually bring a knowledgeable person who can determine whether or not there's something that you might actually be drilling through before you do that kind of thing. It's a potential catastrophe. It's rare, but it's a potential catastrophe.
Got it. And then what about that's for like coring all the way through,
Mm-hmm.
but the solutions where I think it was called
Like a duct?
Yeah, the ones that the metal backed thing.
Mm-hmm.
Like let's say you don't want to have a metal backed thing on top of the floor because then it could be a tripping hazard.
Right.
They kind of like drill not so deep.
Right, but core out a
Like from the wall to the middle of the room, so you can have a
right. That's a big no-no in an existing building. That would be a big problem structurally, definitely. So no, you wouldn't do that. You would. You wouldn't do it without checking with someone. So like I said, it's not a coincidence that they did that on our campus. They did it on the slab on grade because that wasn't an issue for spanning. The chore of that slab is different than one that would span. So you could do it on slab on grade. I don't know another scenario where you would even think about doing it in an existing building. I suppose if you knew it was coming beforehand, you might tell your structural engineer that you're going to do that and he could make the whole rest of the structure work, but I don't think that would be an efficient way to do things either. I think typically you would just bury it, if it was a new building, you would bury it in concrete, you would use a cellular metal floor raceway, um, or you would use, go through the ceiling from below or something like that.
So even though you're not going so far deep, and even though you're not interacting with one of those
that would be
extension cables.
Yeah, because you're essentially you're scoring you've all built models in architecture school, and if you score the chipboard or the corrugated cardboard, right, its ability to span is shot. It just will fold there, and so I would treat it like a score. And so I think, not knowing the specific condition, but if I had something that was spanning, no, I wouldn't. This would not be a good. Running a duct like that would not typically be a good solution. Now, I suppose if you were doing a loft that was an old industrial building that was crazily overstructured, where you had 18-inch thick floor plates, because there used to be a giant piece of machinery on that third floor, and now you're putting a loft on there, and so it's multifamily residential, which has a much lower load. If it was something that was crazily overstructured, I suppose it may be possible, but I'm not comfortable in making that call either way. That's a structural engineer's call.
Got it.
Anybody else?
I have one question if anybody else does not have a question.
Go ahead, fire away.
Alright, so you gave us like an overview of all the flavors of different type of wiring strategies for a floor or to provide electricity to a desk in the middle of the floor.
Mm-hmm.
Now, if I give you a scenario, if you could please tell me what would be the best option for that.
Sure.
It's an existing building and it's an office park building, so tenants change all the time.
Mm-hmm.
And then there's a new tenant who wants to move in like tomorrow or maybe the next week. And the landlord wants to install provide wiring in the middle of the floor, the fastest way but the cheapest way.
Right.
So I guess under carpet is one option, it sounds like. Is there any other option other than that?
Yeah, I mean, there's this nasty one that you could trip over.
Oh, the pole?
No.
Oh, access floor.
No. This one.
Oh, this one.
Yeah,
Okay.
that's the cheapest quick. That's the
Those
cheap.
are really two options, really?
Yeah, right? I mean, you'd think, if you have an industrial design background or know someone from school who does, then by all means, I'm looking for the name of hold on one second. There's a name for these, and they're called metal backed somethings.
I think I've seen them.
Yeah, I'm just looking at my notes, so if you came across them.
Also, if you have a carpet floor and you have under carpet wiring, and you want to change it to a hardwood, would you be able to add sleepers and then provide wiring underneath? Do you think that's
Yes, you can do that. And in fact, we had a really good architect. I wish I remember what his name was. Because I'm on a university campus and because we have a pretty robust guest speaker rotation, someone came a few years ago and he showed just a really elegant way of doing it. So what he did is he did some kind of combination of this with the raised access flooring, some kind of hybrid between that. Yeah, it was basically like that, but it was substantial. So he had let me draw, I'll draw it the best of my memory. Oh man. So August 6th we're going to do bidding, it looks like. So what he did, let's see if I can remember. So he ran sleepers, like you were saying. He ran sleepers like this. And then he put a wood floor here, a really nice wood floor. And so a lot of these like more expensive systems are because you have a gallery or a museum or a higher end office building and you just don't want a raised access floor and you don't want carpet. and you don't maybe have access, you don't want to drop ceiling in the ceiling below and so forth. So he had a wood floor here, and he had a series of these, let's say they were 2x2s or 3x3s, that were supporting those as sleepers, and then he had like a little, I think he had like a little one here, and then he put like a really nice kind of, I don't remember if it was copper or if it was like steel grate, but there was something kind of nice and metally there. And so he used that to run not only conduit, but also air conditioning. So then everything else, so all the air conditioning ducts could be run in the sleepers. The primary ducts were here. And you can imagine, I mean, when you think about these systems, especially the mechanical, especially the air systems, if you can think about them early enough, you can get rid of all that nastiness. And that's what he had done. And he said it was less expensive, is what he had claimed, than a typical drop ceiling and a typical finished floor, because it was all the same. All this wood floor was a finished floor he wanted anyway. And it was just basically the cost of the sleepers and some planning ahead of time to make sure that you could run a main duct this way, and then the secondary ducts would come out this way, and then they had diffusers for the air that would just kind of come out in the floor.
So is this an economical option, you would say?
Yeah, absolutely, especially if you want thermal comfort. So then if instead of having a drop ceiling and having a diffuser in there and having air come out and having her be hot and her be cold, and have the complaints, this one can open up each one of these can open up or close as needed. And maybe it was even a plenum under there, so maybe it was even positively charged. So the air maybe it was just dumped out in there, and then it was, each person has control. So there's a ton of thermal control. So he had claimed it was an economic solution, but it's easy to claim it's an economic solution because it depends what you're comparing it to. So it may not be the economic solution at the kind of level of your client, but yes, you can totally do sleepers, and I wish I had talked about that before, because that is a totally legitimate option. I think a lot of times, because architects don't have a background in this stuff, they just kind of leave it up to the products and the engineers to just tell them what to do, and the engineers will almost always do what they did last time, and as long as they didn't get sued last time, they're going to give you what they had before. And so,
and are the poles an economical option, or I know that you mentioned they were
I doubt. Generally, if you don't see something very often and it's a product, it's probably not economic.
Okay.
So and there are questions in the exam, all over the exam, that ask you about the economics of things, and if you get one of those, if you come across one of those questions, my advice is always to to assume the one you see the most often in practice is most likely the most economic. So plywood versus OSB as sheathing, well, you see OSB more often, so it's probably OSB. Regular, steel versus stainless steel, well, you see regular steel more often used, so it's got to be, regular steel. Let me think of some other examples that you kind of see every day. I mean, carpet versus wood flooring. In a cheap building, you often see carpet, and so you can kind of assume that carpet is probably less expensive. And hardwood versus softwood, and these kind of questions. If you understand what they are, just think back to which you saw most recently, and 9 times out of 10, that's going to be the one that's less expensive.
Thank you.